In 3.7, we pause. We're not learning any more derivative rules here. We're going to look at some rates of change applications. These applications, in a sense, they're not new. We're going to be looking at a lot of like velocity and acceleration, that sort of thing. But it's good to kind of spend some time talk about them. Really, the lecture here is just a bunch of examples of different styles. Keep in mind, we consider these light applications. We get into the heavy applications after the midterm. Okay, 3.7. Let's recap. What do we need to know? So I showed, we know this from before, showed it to you already. The position is typically given as the function s of t. Velocity we think of as v of t, and that is the derivative of position. And then acceleration is a of t, that is the second derivative of position, or you could even think of it as the derivative of velocity. Okay, our first example is this right here. Says a particle moves along a straight line with position s of t equals negative sine of pi t over 4, where t is between 0 and 8, s is in meters, and t is in seconds. So if you picture this, all we have is a straight line, maybe like a number line, like maybe 0 is right there. And so for 8 seconds, this particle moves along the line. And really what's going to happen, because it's a sine, and this, just to kind of picture what's going on. So at time 0, it's at 0 for this one, and then it's going to start, and sine oscillates, right? So it's going to start to move, and it's going to kind of wave back and forth. Just move back and forth on that line. Really exciting. We really want to study this. Just kidding, but it's, we got to get started somewhere, right? Okay. What's the question? What is the velocity of this particle at 3 seconds? 3 seconds after it starts moving, what's the velocity? Well, we know velocity is the derivative of position, so we're going to take the derivative of this, and once we have that derivative, then we're going to plug in t equals 3. So here's the derivative. Let's talk through it. The negative is like a constant multiple, so that negative just carries along. Then we've got a chain rule, right? So we've got an outside and an inside. Derivative of the outside, the sine, is cosine. And for the time being, we just copy the inside function. Then we multiply by the derivative of the inside, and that's pi over 4. Let me explain this, because that can be kind of tricky for people. Pi t over 4, the derivative is just pi over 4. Why is that? When you see pi t over 4, a lot of people think to use quotient rule, right? There's a high and a low. And there's nothing wrong with that. You can definitely get to this answer with the quotient rule, but I'll tell you it's actually simpler than that. Because your denominator is a constant, why not just think of this as pi over 4 times t? And then you're like, oh, well, the derivative of this, pi over 4 times 1, that's just pi over 4. That's so much easier to think of it that way than with the quotient rule. Okay, so in any case, that's our velocity. Let's clean that up. We can move maybe that pi over 4 out front. That looks a little bit better. Negative pi over 4 times the cosine of pi t over 4. All right, then we plug in the 3. And if you haven't already, grab a calculator. Unless you want to do this from memory. V of 3 is negative pi over 4 cosine, and if the t is a 3, let's just call it 3 pi over 4. Cosine 3 pi over 4 is root 2 over 2. Negative root 2 over 2. And so the negatives would cancel, and we get pi times root 2, and the 4 times 2 gives you 8. we're just going to leave it like that. That's the exact velocity, pi root 2 over 8. Whenever you're working with position, velocity, acceleration, you want to give units on your final answer. And here it's meters per second. How fast is it moving, right? Meters per second. Okay. All right, there's the velocity at 3 seconds. Let's move along. We got several parts to this question. The next one is, at what time or times is the particle at rest? Okay, again, what's happening? The particle, it's going to start to move. Maybe it starts to move in the positive direction. It might start to move in the negative direction. We're not sure. But whatever the case, it's going to start to move, and then it's going to start to slow down and then stop and then turn back around the other direction and then slow down and then stop and turn back around the other direction, right? Go back and forth because of the sign. So when it stops and turns around, it's at rest. It slows down, then goes the other way. Well, how can we find that, algebraically or with calculus? At what time is the particle at rest? That's when the velocity equals 0. Well, of course. All right, so we know what the velocity is already. Right. Negative pi over 4 cosine of pi t over 4 equals 0. What value of t, or maybe there's more than one, will cause the velocity to equal 0? Let's solve this for t. Well, we can divide by that negative pi over 4. That's gone. So cosine pi t over 4 equals 0. And then we'll have to think to ourselves, okay, when will the cosine equal 0? What might this equal right here? The cosine of what gives 0? And if you think about it, maybe you guess and check in your calculator. Maybe you like to draw out the graph of cosine. Maybe you like to use the unit circle. Somehow, we need to realize that what's inside here could equal pi over 2, or it could equal 3 pi over 2. At least those are the values in the first period of cosine that would cause it to equal 0. We might need more. We'll see what happens. Okay, so let's set up two equations here. Pi t over 4 equals pi over 2. Pi t over 4 equals 3 pi over 2. And solve these both for t. And we get these answers, right? Multiplying by 2, dividing by pi. Same idea. We get t equals 2 and t equals 6. We know that these are the only two answers because they said at the beginning that t is between 0 and 8. So if we were suspicious that there might be more answers, then we could list some other, keep going into the second period of cosine and keep solving for more values of t. If we did that, then we would go beyond 8 in our solution. So we know to stop here. It happens at these two moments, at 2 and at 6 seconds, if we're limited to just 0 and 8. Okay, let's keep going. There's more. Kind of building off that last question, over what time intervals is the particle moving in the positive direction? All right. At what time intervals is the particle moving in the positive direction? So I'm going to draw, yeah, that's good to note. When you're moving in the positive direction, that means your velocity is positive. It is possible for velocity to be negative if you're moving in the negative direction. So maybe we think if it's moving this way, it's positive. If it's moving this way, it's negative. Okay. Here's what we're going to do. We know this thing only operates between 0 seconds and 8 seconds. So I'm going to create this number line from 0 to 8. We're also going to mark off the 2 moments when the particle is stopped. So at 2 and at 6, it's not moving at all. It has a 0 velocity. So what's happening is, between 0 and 2, it's moving in one direction. We don't know which one. But then at 2, it stops and it begins moving in the other direction. So maybe it comes out, stops, starts moving back until it gets to 6 seconds where it stops again. And then for those last 2 seconds, it moves back the other direction. But we're not sure if it's here and then here and then here, or maybe it started going backwards and then forwards. Okay, how can we tell? Here's what we're going to do. Here's one approach that just allows us to plug in some numbers. We're going to check a value from each of the 3 intervals in the velocity. So we'll check a number between 0 and 2, between 2 and 6, between 6 and 8. Plug them into the velocity, and we're just going to see if we get a positive or a negative result. So I'm just going to show you all this because it's just a little plug and chug, they say. Let's start with that first interval. We need to pick something between 0 and 2. Well, a good choice would be 1. What's happening at 1 second? If we plug that into velocity, negative pi over 4 cosine, it'd be pi times 1 over 4. Okay. This is root 2 over 2, so that makes the whole thing negative pi root 2 over 8. Now the thing is, we're really not concerned about the number, just is it positive or negative. This one turned out to be negative, so we know for that interval, the velocity is negative. Which, if you think back here, oh, okay, it actually moves back this way during the first 2 seconds. Then it stops and starts going back the other direction. So let's look at what's happening at 4. You know what? I suppose it's possible that it stops and then continues in the negative direction. So I shouldn't say we know it turns around. But okay, so we're going to plug in 4 into our velocity. That would be pi times 4 over 4, or just cosine pi. Cosine pi is negative 1, so that gives us pi over 4, and that's positive. Okay, so it is, so like it's moving in the negative direction here, but then here it's moving in the positive direction. So after 2 seconds, it turns around, and for 4 seconds, it goes back. Maybe we draw it up here. It goes back this way. Then at 6 seconds, it stops, and let's check what's happening at 7 seconds for that last interval. Turns out it's the same result as back here. Cosine of 7 pi over 4 gives you negative pi root 2 over 8. It's negative again. So for that last piece, it's going back this direction just for a couple of seconds. I think it winds up back at the origin. Okay, so when is the particle moving in the positive direction? Between 2 and 6. Very nice. I've got one more question from this example. Part D. What is the acceleration of this particle at 2 seconds? Okay. So we know at 2 seconds it came to a stop and then turned back around. But just because it stopped, it only stopped for an instant. It didn't sit there for any amount of time. It stopped and turned around. So there is an acceleration right there. It is changing velocity constantly, even though for an instant it paused. So what's the acceleration at 2 seconds? Well, we really don't even need to think through all that necessarily. We need to take the derivative of the velocity. So here's the velocity again. And here's its derivative for acceleration. A of t. Okay, where did this come from? Well, our constant multiple got copied. Then we've got a chain rule. So derivative of cosine is negative sine, and this gets copied, and then the derivative of that we know to be pi over 4. And so acceleration, the negatives cancel, and we've got pi times pi, 4 times 4, sine pi t over 4. Only last thing to do is plug in the 2 seconds. So a of 2, pi squared over 16 times the sine of pi over 2. And you may know that the sine of pi over 2 equals 1. And so our answer here is pi squared over 16. We're just going to keep it like that since they didn't tell us to round. Hey, I forgot to put the units on the end. Maybe you know the units of acceleration here would be meters per second squared, meters per second per second. There it is. Okay, let's stop here. I got a couple more examples coming up.